Let's take a minute to talk about what changes if we switch our device to having an N-type substrate as opposed to a P-type substrate. So as you can see in this drawing down here, I now have this N-type substrate and we have P plus regions as opposed to N plus regions. And so again, remember the plus just indicates that it's a little more heavily doped. We still have the same structure with our metal and our oxide on our gate terminal. And so typically, like with our P-type substrate, we're going to have our source connected to ground, and typically we're going to tie the substrate to that source as well. Now, because this is an N-type substrate, now we need to have a negative voltage applied to our gate in order to create that inversion layer. So we kind of touched on that a little bit when we talked about our MOS capacitor, but physically what we could do is we could think about having a battery oriented like this, such that we're applying the negative terminal to our gate voltage with respect to our source. And so this voltage would then be our VSG. So similarly, once we've done that and we've created our inversion layer, so we would have an inversion layer of holes. So let's go ahead and sort of draw that here. So this would be our inversion layer of holes. And so we talked about that just briefly with our MOS capacitor. And once we have that, then we can apply some voltage between our drain and source in order to move holes between our two hole reservoirs with our P plus regions. So in order to do that, we can apply some potential which is negative at the drain with respect to the source. And so we then have this voltage which is VSD. And so once we do that, of course, we can see that our holes are going to be flowing from the source to the drain in this direction. And so what that means is our conventional current, which is in the same direction of our holes, is going to be coming into the source and out of the drain. So we see that's opposite from the direction of our P-type substrate. So again, same basic operation principles. In this case, we need a negative gate voltage to turn on the device. So negative gate voltage to turn on. And so we're assuming that we have an enhancement mode device. We can also have a depletion mode device where we already have that inversion layer with no gate voltage. But for what we talked about above, we have an enhancement mode device. And so because we have now a channel of holes, an inversion layer of holes, we'll often refer to this as a P-channel device, or even shorter, we can also call this a Pmos device. So now we have Pmos as well as NMOS, depending on what type of substrate we have. And so it can be a little confusing, but of course we see because we have an N-type substrate, this is Pmos device. In the textbook, so just like with our P-type device, there is some threshold value of this source to gate voltage. And so in the textbook, the notation for that is VTP. So we have VTP is going to be our threshold voltage, and it has the same underlying definition that's going to correspond to the point where we have what we call strong inversion in this region of our channel. Again, we've already talked about how the current flow is sort of opposite from our N-channel device or our NMOS device. So now that we have sort of this basic understanding of the differences and how our voltage polarities are different, we can talk about equations for our Pmos device. So let's go ahead and talk about our Pmos equations. So again, same basic idea. If we were to draw a family of curves, we're still going to have our non-saturation region and saturation region, which are going to be separated by some saturation value of VSD. So we have non-saturation and saturation regions. Which are going to be separated by this saturation source to drain voltage. So now because we have P channel, we have VSD as opposed to VDS. So VSD sat is going to be VSG. So again, we see our polarity is a little bit different, plus our VTP. So big difference there is now we're adding that threshold voltage as opposed to subtracting like we did for our NMOS. Keep in mind, however, that for an enhancement mode device, that VTP is going to be a negative value, so the effect is still the same. So let's talk about then our equations for a non-saturation region. So if we're in the non-saturation region, then we're going to have our VSD is going to be less than our VSD sat. So that's sort of the same basic idea if we were looking on the family of IV curves. So we're sort of to the left of that transition curve corresponding to VSD sat. And so our equation for ID looks very similar as you might expect. So we have now Kp, and we'll come back and define that clearly in a minute, times 2 VSG plus VTP, all of that times VSD, minus VSD squared. So again, very similar, just slightly different based on our different polarities, and now you'll notice we're adding that threshold voltage as opposed to subtracting like we did with our NMOS. So now we can look at our saturation region as well. So you notice again, of course, we're not deriving these equations, we're just stating them, and we want to make sure we're comfortable using them. So for our saturation region, we now have VSD is greater than our VSD sat value. And the equation again is very similar to what we saw before. So our ID, our drain current, is equal to Kp times the quantity of VSG plus VTP squared. So now let's come back to that Kp. So again, Kp is our conduction parameter. So Kp is still our conduction parameter. So same terminology we had for our Kn. And the equation is essentially the same. We just have one minor change. So we have the width, and now we have our hole mobility as opposed to our electron mobility, because of course our holes are what's creating our current as they move through that inversion layer. And so of course we can define that with this lowercase k sub p over 2 divided by, multiplied by our W over L. Again, just to emphasize that we have this dependence on electrical characteristics as well as device geometry. And so the only term that's different that we haven't seen before, of course, sort of implicitly this Kp primed is new, but same basic parallel to our Kn. The only new term is this mu sub p. And so as I said a second ago, that mu sub p is our hole mobility in the inversion layer. And so just like we saw in the bulk of devices, typically that hole mobility is going to be less than our electron mobility. So typically our mu sub p is going to be less than mu sub n. So now we are equipped with equations to handle any type of device, Pmos, NMOS, enhancement mode, depletion mode. And I would recommend you take a look at the table on page 141 in the textbook. And so that's table 3.1, because it has a really nice summary of all of these different equations, very succinct, all in one place. So that could be a good reference as you're creating your note sheets and as you're studying for exams or working through homework.